Hello everyone, welcome to this lecture. So, we will continue our discussion regarding randomized protocol for Byzantine agreement. So, we will see the framework due to Benor and Rabin, how we can combine the vote and coin primitives to get a Byzantine agreement protocol with a constant expected number of rounds, and we will do the analysis of it. So, let us first see the vote protocol, instantiation of the vote protocol, and this instantiation will be perfectly secure and it will be with n greater than 3t. Okay, so, there can be at most t corruptions, t Byzantine corruptions, and n is greater than 3t. Okay. So, the protocol is very simple, it is a single round protocol, it is a one round protocol where each party just has to send its input to everyone else, that is all, including itself. Okay. And the output decision is made as follows: every party PI checks that if it has received a copy of some bit p at least n minus t times from n minus t different parties. If that is the case, then it outputs that particular bit p, otherwise it outputs a spot. Now, we make some claims regarding this simple vote protocol. So, the first claim is that if all the honest parties have the same input, then everyone outputs that bit p. Okay. And the proof is very simple. If every honest party have the same input b, and remember we have at least n minus t honest parties. Okay. That means at the end of the round, every honest party will receive at least n minus t copies of the bit p, and there could be at most t corrupt parties who can send b prime as their inputs. Okay. And what is the output decision rule? The output decision rule is that if a bit is received from n minus t parties, output that bit, and that is why every party will output b and not b prime, and no honest party will output bot, because there is a bit b which is received at least n minus t times. The second claim is that if any honest party outputs a bit b, right, then every other honest party will also output either the same bit b or bot. Right. So, there is a difference now between the two claim statements. In the first claim statement, the hypothesis was that all the parties had the same input. In that case, everyone will output that bit p. The second claim states that it could be possible that even though all the honest parties do not have the same input bit p, but it could be possible that still one of the honest parties output a bit p, which could be either 0 or 1. If that is the case, then no other honest party will output b prime. The only output for the other parties could be either the bit p or the value bot. So, again we have proved this claim several times in the past, earlier in the context of phase king broadcast protocols and so on. So, the idea behind the proof is as follows. So, imagine there is the party pi, and say the party pi outputs the bit p. Now, since pi outputs the bit p, that means in the protocol pi would have received the bit b from a set A of n minus t parties, okay, at least n minus t parties, and among those n minus t parties at least n minus 2t are guaranteed to be honest. Now, those n minus 2t honest parties in the set A will also send b as their input to every other honest party pj. So, consider another honest party pj different from pi, and let us see how many copies of b pj will receive and how many copies of b prime pj might receive, and let us see what could be the possible output for pj. So, sorry for the typo here, it should be p sub j. So, the party p sub j may receive the complementary bit p prime from at most 2T parties. Who can be those 2T parties? There could be up to T corrupt parties in the set A, T corrupt parties in A may send B prime to Pj, right, because they are corrupt, right. They can send B to one honest party and they can send B prime to another set of honest parties, and there could be up to T honest parties outside A. So, altogether there could be at most 2T parties who may send a bit B prime to the honest party Pj. Now, what is the output decision rule? Well, Pj would have output B prime provided it would have received n minus t copies of B prime, but 2T is strictly less than n minus t, because we are working with the condition n greater than 3T. That means, if at all Pj outputs a bit, it has to be B, it can't be B prime, or otherwise Pj would have output bot. So, either Pj would output B or the value bot, but it can't be B prime, right. So, that is a vote protocol. Now, we will give an instantiation of the coin protocol with n greater than 3T, and our instantiation will be cryptographically secure. That means, it will be secure only against it will be secure only against a computationally bounded adversary. Okay. As a result of that, when we will apply this instantiation of coin protocol in the framework of Rabin and Benor, the resultant BA protocol will be cryptographically secure. Later on, once we discuss advanced primitives, advanced tools, we will see an instantiation of the coin protocol which is perfectly secure. So, since we are assuming here a computationally bounded adversary whose running time is polynomial time, we are free to use cryptographic tools. So, we will assume a digital signature setup for every party, similar to what we have done in the Doleb-Strong protocol, and the setup will be that every party Pi will have its own signing key, and the verification keys of all the parties will be publicly known. This will be a one time setup which can be used for polynomially many instances of the coin protocol. Okay. Apart from that, apart from this setup, we will also use a cryptographically secure hash function, say H, which is modeled as a random oracle. So, I am assuming here that all of you know what is a cryptographically secure hash function. If you are not aware of what is a cryptographically secure hash function, you can refer to any standard text on cryptography, or you can also refer to my NPTEL course on foundations of cryptography. Basically, hash function is a function which takes inputs of any size and gives you outputs of some fixed size. Okay. And there are many security properties which we require from the hash function. The primary being the primary security property that we require from the hash function is the collision resistance property. namely it should be difficult to come up with two different inputs x1 and x2 which are not same, but their hash values are same. That should be difficult, even though there are multiple such x1 x2 in the domain, because we are our domain could be infinite, but codomain is finite. So, from the pigeonhole principle it is straightforward to conclude that there will be multiple such pairs of values x1 x2 which are different, but having the same hash value, but collision resistance demand that it should be difficult to come up or identify or find such pairs in polynomial amount of time. When I say that we are modeling the hash function as a random oracle, that also means we are making a very strong assumption regarding the property of the hash function. Random oracle means here that we assume that H behaves like a random function, true random function. That means hash of x1, hash of x2 are all independently are all independent values, are all random values. Okay. And they are unpredictable. That means if I am the adversary and if I know the description of the hash function, but the input for the hash function I do not know beforehand, then for me the output of the hash function on that input is unpredictable. Okay. So, there are several instantiations of practical instantiations of hash functions available which you can use while instantiating this coin protocol. So, you can use the SHA function family, SHA function hash functions, SHA family hash functions. Okay. So, that is a setup, right. So, digital signature setup for every party and a hash function publicly known which is treated like a random oracle, and apart from that as part of the setup a publicly known uniformly random string is also available to the parties. That is also a one time setup which can be used for polynomially many invocations instances of the coin protocol. Now, suppose we want to instantiate the coin primitive coin protocol for the kth iteration. So, where k is a input parameter here, and looking ahead when we will be using this coin protocol with the vote protocol in the framework of Benor and Rabin. Recall that in that framework there are several iterations where in each iteration there is one instance of the coin primitive and two instances of the vote primitive. So, you can imagine that if we are instantiating the coin primitive during the kth iteration, this will be the code which is going to be executed. Okay. So, each party pi during the coin protocol for the kth iteration will do the following. It will send the value vi, a tuple of values, to everyone. So, what exactly this tuple vi consists of? It consists of the identity of the party, the value of the random string, the iteration number and the signature of the ith party on the string r followed by k. Okay. If pi is an honest party, it will send this value vi, this tuple vi identically to everyone, but if pi is a corrupt party, it may not follow the protocol. It may send vi to one set of party, it may send another vi to another set of honest parties, or it may not send any vi at all. So, it can behave in any arbitrary fashion. Now, once every party sends its tuple vi to every other party, what the party pi does is the following. It would have received the tuple vj from many parties, at least from all the honest parties it would have received the corresponding tuple Vj. It verifies whether the tuple Vj is correct or not, is as per the protocol. And how it can verify? So, suppose for instance, it has received this tuple V1. Now, V1 is supposed to consist of the identity of the parties, it checks that. It should have the value of the random string, anyhow that is publicly known. So, PI can verify that. It should check the iteration number, that is also a public information. And what is the only thing which PI has to check separately is the signature, and that also can be verified because the corresponding verification key for the party P1 is publicly available. So, PI whenever it receives a tuple Vj from any party Pj, it can verify it whether it is correct or not. If it is correct, then it keeps it, otherwise it simply considers that Pi has not sent any value, Pj has not sent any value, or imagine that it has sent some default message. Now, let Pm be the least indexed party such that among all the tuples which are received by Pi, the hash value of the mth party's tuple is the least one. Okay. So, again what we are doing here is that we are asking the party Pi to compute the hash value of all the v values that it has received. Now, remember H is modeled as a random function. So, it could be possible that there are two tuples which Pi has received which results in the same hash value. So, what Pi is doing is it is looking for the least indexed party whose hash value is strictly less than equal to whose hash value is less than equal to the hash value of the tuples of the other parties. Okay. So, imagine Pm is the least such indexed party. Now, what is the output for the party Pi? It simply outputs the LSB of the hash value, that among so there will be the least LSB for all the hash values that it has computed. Among those least significant bit, Pi will be considering the LSB only for the tuple corresponding to the party Pm, whose hash value is less than the hash values of all the other parties. So, again you can see that this coin protocol is a one round protocol. Because it requires each party to send only the tuple Vi, and rest of the steps are local computations. So, that is a simple coin protocol. Now, we will analyze it. Okay. So, the first claim here is that if we consider the hash values of all the tuples V1, V2, Vn, they are random strings from the codomain of the hash function. And this simply comes from the fact that we are assuming the hash function to behave like a random function or random oracle. The second claim is a slightly stronger claim, which states that if we consider the hash values of all the tuples received from the parties across all the instantiations of the coin protocol. So, remember that coin protocol takes also as input the iteration number k, right. So, the statement basically says that if we take all possible instantiations of the coin protocol, and in every instance of the coin protocol, the parties would have computed the tuples V1, V2, Vn and their hash values, right. Similarly, in the second invocation, the parties would have computed the corresponding tuples, exchange and computed the hash values. Similarly, during the kth invocation of the coin primitive, the parties would have exchanged the corresponding v tuples and computed their hash values, and like that in every iteration they would have computed the corresponding v tuples and exchange them and compute the hash values. So, what we are claiming here is that if we take the hash values, they will be independent of each other across all the iterations. So, that means if we consider, say for instance, the invocation k and invocation k plus 1 of the coin primitive, then none of the hash values which are computed during the kth invocation will have any dependency on the hash values which are computed during the k plus 1th iteration. And this simply comes because of the fact that in every iteration the hash values are computed on a tuple which are guaranteed to be different if the party who is computed them are different. So, for instance, if the ith party is computed tuple and if the jth party is computing the tuple, then either the party indices will be different, whereas it could be possible that we are talking about say h of v 2 and h of v 2 in the two consecutive instances of the coin primitive. So, both these hash values will be depending upon the party p 2. So, in that case also there will be at least one component in the corresponding v tuple which will be different. So, for the kth instance of the coin primitive, the k component of the tuple will be k, whereas the corresponding component in the k plus 1th instance will be k plus 1. So, either the party indices will be different or the iteration number will be different. Okay. And that ensures that the hash values are computed for different tuples across all the iterations, even if we consider the same party. So, that means even if I take say the party number 1 and if I focus on all the v 1 tuples which are computed by p 1 across all the instances of the coin primitive, they are going to be different. Because the iteration number will vary, and since the tuples are different and we are assuming that the hash function is behaving like a random string, that means the hash function since we are assuming that the hash function is behaving like a random functions, and since the tuples are different across different iterations, the hash function when applied on those different tuples will result in independent outputs. Okay. So, there is absolutely no dependency on the hash outputs which are computed during different invocations of the coin primitive. So, basically through this claim what we are stating here is that if the adversary has seen a set of n hash values during some invocation of the coin primitive, then in the next iteration it can't cook up its v tuples so that its hash value results in some specific value which adversary would like to get. That is not possible. Okay. So, these are the two claims regarding this coin protocol. Now, the third claim is that let P m be the least indexed party such that the hash value of its tuple is less than equal to the hash value of all other tuples corresponding to the other parties. Then the probability that P m is an honest party is at least 2 over 3. And this comes from the fact that the hash values of all the tuples are random strings and independent of each other. So, that means now among the n parties, if we focus on the set of bad parties and the set of good parties. So, suppose H is the set of honest party and B is the set of corrupt parties, then the ratio of the set of honest parties over the set of all parties is at least 2 over 3, because we are assuming n is greater than 3t. So, 2/3 of the parties are honest and 1/3 of the parties are corrupt. And since the hash values of all the tuples are independent of each other, random strings, that means the LSBs are also random. Okay. So, that means if I focus across the LSBs of all the hash values computed during the coin protocol, they are a random string, and what we want to analyze here is that what is the probability that the party PM whose hash value turned out to be smallest belongs to the set H. Well, the probability of that is 2 over 3, because there are total n number of parties and 2/3 of them could be honest. This automatically imply that all honest parties output a common random bit with probability at least 2 over 3. Okay. Why that is the case? Because with probability 2 over 3, the honest party the party PM whose hash value turned out to be the smallest one belongs to the set of honest parties. It is only with probability 1 over 3 that PM belongs to the set of bad parties. Now, if PM belongs to the set of bad parties, then this claim, then it is not guaranteed that all honest parties have the same output bit, because what the party PM can do is the following. If PM is a corrupt party, then it can do the following. So, in the protocol, every party would have sent their V tuples to every other party. So, if PM is a bad party, then what it can do is it waits for all the V tuples to reach to PM, and it has not yet computed, and it has also computed its V tuple, say VM, but right now it has not sent its V tuple to any other party, it is holding it. Now, since it has all the n V tuples, what PM can do is it checks if H of VM is the smallest among H of V1, H of V2, H of Vn. It checks that, and if it finds that indeed H of Vm is the smallest among all these hash values, then it can decide to do the following. It can send Vm to one honest Pi, but it does not send anything, it does not send a tuple Vm to another honest party Pj. This will result in the following scenario. So, Pi, it will have V1, V2, Vm, Vn, all of them, whereas Pj will have V1, V2, it will not have Vm, and it will have all other tuples. Now, for Pi, it is the tuple Vm whose hash value will be the least. So, it will output the corresponding LSB, but for Pj it will be some other tuple whose hash value turned out to be the smallest, because the tuple Vm whose hash value is supposed to be the smallest among the list is not available with Pj, because the corresponding corrupt party PM has decided not to send it to Pj, in which case the bit which Pj is going to output will be different from the bit which Pi is going to output. This happens only if Pm is a corrupt party, which can happen with probability 1 over 3. Of course, if Pm belongs to the set of honest parties, then Pm will not do any such thing. It will send the tuple Vm both to Pi as well as to Pj, and both Pi and Pj will find that it is Vm whose hash value turns out to be the smallest, and both of them will output the same bit, and the probability of that is 2 over 3. And that shows the commonness probability for this instantiation of this for this particular instantiation of the coin primitive is 2 over 3. Okay. So, that concludes this lecture. So, we have seen the instantiation for the vote protocol, which is perfectly secure. So, the vote protocol is perfectly secure. And our coin protocol is cryptographically secure. Okay. Both are designed with n greater than 3t, and both of them is a one round protocol. So, vote protocol is also a one round protocol, coin protocol is also a one round protocol. In the next lecture, we will see how we club these two protocols, two primitives, vote and coin, in the framework of Rabin and Benor, and get the exact Byzantine agreement protocol. So, the instantiation of the vote and the coin that I have discussed today is taken from this manuscript. Thank you.